Hello students, today we are going to discuss about non-aqueous solvents. Today's topic is non-aqueous solvents. This is Muhammad Jalil Ahmed, lecturer in chemistry, Dr. BRR Government Degree College, Jadcherla, Mahbubnagar district. What are called non-aqueous solvents? Aqua means water. Those solvents which are other than water are called non-aqueous solvents. Water is called a universal solvent. Why? Because water dissolves many compounds. Many compounds means inorganic compounds as well as organic compounds are soluble in water. Since majority of the compounds are soluble in water, water is called a universal solvent. Now, today we are going to discuss the solvent other than water. Those solvents other than water: liquid ammonia, liquid ammonia, liquid HF, liquid SO2, etc. are the various examples of non-aqueous solvents. In this topic, we are going to discuss classification of non-aqueous solvents, types of non-aqueous solvents, physical properties of non-aqueous solvents, reactions of non-aqueous solvents. Introduction. An inorganic non-aqueous solvent is a solvent other than water that is not an organic compound. Non-aqueous solvent is not an organic compound. It is a solvent other than water. Examples are liquid ammonia, liquid sulfur dioxide, sulfuryl chloride, phosphoryl chloride, antimony trichloride, bromine pentafluoride, hydrogen fluoride, other inorganic. These are the various examples of non-aqueous solvents. These solvents are used in chemical research and industry for reactions. Now, classification of solvents. Classification of solvents based on proton. Classification of solvents based on polar and non-polar solvents. Classification of solvents on aqueous and non-aqueous solvents. Types of non-aqueous solvents. We are going to discuss types of non-aqueous solvents. Number 1, protonic and non-protonic solvent. Protonic and non-protonic solvent. What are called protonic solvents and what are called non-protonic solvents? The solvents from which protons can be derived are called protonic solvents. The solvents from which protons can be derived are called protonic solvents. In other words, the solvents which can generate protons, which can produce protons, are also called protonic solvents. We also call them as protogenic solvents. Protonic solvents are also called protogenic solvents. Example: water, H2O. Water can produce a proton. Water can produce a proton on ionization. Therefore, water is called a protonic solvent. Sulfuric acid, H2SO4. Sulfuric acid can also produce protons, or protons can be derived from sulfuric acid. H2SO4 gives rise to H plus HSO4 minus, or H2SO4 gives rise to 2H plus SO4 2 minus. Anyhow, water can produce protons. Sulfuric acid can also produce protons. Therefore, water, sulfuric acid, hydrofluoric acid, etc. are called protonic solvents. The solvents from which protons cannot be derived are called non-protonic solvents. The solvents from which protons cannot be derived are called non-protonic solvents. Example: liquid sulfur dioxide, liquid SO2. From liquid SO2, proton cannot be derived. Therefore, liquid SO2 is an example of non-protonic solvent. Similarly, benzene, C6H6. Even though benzene contains hydrogens, but they are not ionizable. They are not ionizable. Therefore, benzene cannot donate protons, or protons cannot be derived from benzene. Therefore, benzene is called non-protonic solvent. Chloroform, CHCl3. Chloroform, CHCl3. Chloroform also contains hydrogen. Chloroform also contains hydrogen, but it will not ionize. Therefore, though it contains hydrogen, chloroform cannot produce proton. Proton cannot be derived from chloroform. Therefore, chloroform is also called non-protonic solvent. Next, protic or protonic solvents. Protic or protonic solvents. Ammonia. Ammonia undergoes autoionization, producing ammonium ion and amide ion. Similarly, hydrogen fluoride. Hydrogen fluoride also undergoes autoionization, producing H2F plus cation and HF2 minus anion. H2F plus cation, HF2 minus anion. Hydrogen difluoride. 2H2SO4 gives rise to H3SO4 plus HSO4 minus. Ammonia, hydrogen fluoride, sulfuric acid. These are called protic solvents or protonic solvents. Again, these protonic solvents are classified into two: acidic and basic. Acidic are protogenic solvents, basic are protophilic solvents. H2SO4, sulfuric acid, HCl, hydrochloric acid, CH3COOH, acetic acid, hydrogen cyanide, HCN, These acids can produce protons. Therefore, they are also called protogenic solvents. Basic or protophilic solvents. Ammonia is the best example for protophilic solvent. Hydrazine N2H4. Ammonia, hydrazine are the solvents which accept protons. They are proton-loving solvents. Philic means loving, so ammonia can accept a proton from any other substance. Hydrazine can also accept a proton from any other substance. Therefore, ammonia, hydrazine are the examples of protophilic solvents. Next, aprotic or non-protic solvents. Aprotic or non-protic solvents. Benzene, chloroform, carbon tetrachloride, sulfur dioxide. What are called aprotic or non-protonic solvents? Those solvents which cannot generate protons, or those solvents from which proton cannot be derived, are called aprotic or non-protonic solvents. Benzene C6H6, chloroform CHCl3, carbon tetrachloride CCl4, sulfur dioxide SO2. N2O4 dinitrogen tetroxide undergoes ionization producing nitrosonium ion and nitrate ion. SbCl2 antimony dichloride or dichloroantimonium. Antimony dichloride undergoes autoionization producing antimony dichloroantimonium ion and tetrachloroantimonium ion. We call them as dichloroantimonium and tetrachloroantimonate. POCl3 undergoes autoionization producing POCl2 plus POCl4 minus. Phosphorine chloride. Actually, after balancing 2 POCl3 giving rise to POCl2 plus POCl4 minus. Acidic, basic and amphiprotic solvents. Here wrongly printed, not or end. Acidic solvents, basic solvents and amphiprotic solvents. Now, what are called acidic solvents? The solvents which have a tendency to donate protons. The solvents which have a tendency to donate protons are called acidic solvents. Example, acetic acid CH3COOH, hydrogen fluoride HF, etc. Acetic acid and hydrogen fluoride have a tendency to donate protons. Therefore, they are called acidic solvents. Next, basic solvents. The solvents which have strong tendency to accept protons are called basic solvents. They are basic in nature. The solvents which have strong tendency to accept protons are basic in nature and are called basic or protophilic solvents. Already I told you, protophilic means proton loving, proton accepting. Example, liquid NH3. Liquid ammonia is a protophilic solvent, pyridine C6H5N. So liquid ammonia contains a lone pair of electrons over the central nitrogen atom. Therefore, it can accept a proton. It will have a strong tendency to accept a proton. Similarly, pyridine or pyridine. Pyridine has a lone pair of electron over the nitrogen. Therefore, pyridine can also accept a strong tendency to accept a proton. Therefore, pyridine is an example of protophilic solvent. Now, third definition is wrongly printed. Sorry to say, third definition is not correct. In this slide, the solvents which have both tendency to gain and lose protons are called amphiprotic solvents. Amphiprotic solvents or amphoteric solvents. Those solvents which have a tendency to lose protons and have a tendency to gain protons. It means these solvents possess both the tendency of losing of protons and gaining of protons. Therefore, they are called amphiprotic solvents or amphoteric solvents. Example, H2O. H2O can lose a proton, H2O can gain a proton. Therefore, H2O is the best example of amphiprotic solvent. Similarly, C2H5OH, that is ethanol or ethyl alcohol. Ethyl alcohol can also lose a proton, it can also gain a proton. So those solvents which have greater tendency to lose or gain protons are called amphiprotic solvents. Now, ionizing and non-ionizing solvents. What are called ionizing solvents and what are called non-ionizing solvents? The solvents which are capable of undergoing self-ionization or auto-ionization are called ionizing solvents. The solvents which are capable of undergoing self-ionization are called ionizing solvents. Example, water, H2O, ammonia, NH3, sulfur dioxide, SO2, etc. If H2O undergoes autoionization, it produces hydronium ion and hydroxide ion. We can write an equation, 2H2O gives rise to H3O plus OH minus. Similarly, if ammonia undergoes autoionization, it produces ammonium ion, amide ion. 2NH3 gives rise to NH4 plus NH2 minus. The solvents which do not ionize at all are called non-ionizing solvents. The solvents which do not ionize at all are called non-ionizing solvents. Example, benzene, hydrocarbons, etc. Benzene does not ionize, hydrocarbons do not ionize, therefore benzene and hydrocarbons are the examples of non-ionizing solvents. These are non-polar in nature. Fourth type of solvents, coordinating and non-coordinating solvents. Coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. Example, NH3, ammonia, SO2, sulfur dioxide, DMSO, dimethyl sulfoxide, DMF, dimethylformamide, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions of solute are called non-coordinating solvents. The solvents which are not capable of coordinating with the metal ions of solute are called non-coordinating solvents. For example, CCl4, chloride, saturated hydrocarbons. Carbon tetrachloride and saturated hydrocarbons are not capable of coordinating with the metal ions. Physical properties of solvents: melting point and boiling point, dielectric constant, viscosity, dipole moment, heat of fusion and heat of vaporization. So these physical constant values of a solvent decide the nature of the solvent. The nature of the non-aqueous solvent depends on these factors. They are melting and boiling point, dielectric constant, viscosity, dipole moment, heat of fusion and heat of vaporization. If we observe the physical constants of liquid ammonia, which is a non-aqueous solvent, let us see the physical constants of liquid ammonia. Freezing point -77.7 degrees centigrade, boiling point -33.38 degrees centigrade, dielectric constant is 22.08 -33.5 degrees centigrade, liquid range -77 to -33 degrees centigrade, heat of fusion is 0.018 kilojoule per mole, heat of vaporization is 23.6 kilojoule per mole. Self-ionizable in nature. Liquid ammonia undergoes self-ionization or auto-ionization. Liquid ammonia acts as an associated solvent. Now, why ammonia acts as a better solvent than water? Why ammonia acts as a better solvent than water? Due to these reasons, due to the following reasons, ammonia acts as a better solvent than water. First reason is poor conductor of electricity. Ammonia is a poor conductor of electricity. Specific heat of ammonia is greater than water. Specific heat of ammonia is greater than water, and liquid ammonia is less viscous than water. Liquid ammonia has high critical temperature and pressure. Liquid ammonia is less associated than water. Why? Because in liquid ammonia, lesser hydrogen bonding is observed. Due to formation of strong reducing metal ammonia solutions with alkali metals, it means liquid ammonia readily reacts with alkali metals, forming metal ammonia solutions. These metal ammonia solutions act as strong reducing agents. So due to these reasons, ammonia acts as a better solvent than water. Now, chemical reactions. Acid-base reactions, precipitation reactions, redox reactions, solvation reactions. Types of reactions in non-aqueous solvents. Number 1, precipitation reactions or metathetical reactions. The reactions in which precipitation occurs on mixing two solutions are called metathetical or precipitation reactions. The reactions in which precipitation occurs on mixing two solutions are called precipitation reactions. Example: when AgNO3 solution is mixed with BaCl2 solution, within no time chemical reaction completes, giving rise to white precipitate of AgCl and BaNO3 twice solution. This reaction is an example of double decomposition. In this reaction, silver nitrate is an ionic compound, BaCl2 is also an ionic compound, and silver ions combine with chloride ions forming silver chloride as a white precipitate. So, since precipitation occurred in this reaction, this is an example of precipitation reaction. Salt formation. Salt formation. The reactions between appropriate acidic and basic substances to form salts are called salt formation reactions. For example, sodium uride cannot be prepared by the action of urea on sodium hydroxide in water because strong base cannot take proton from urea molecule. If you observe the reaction, sodium uride reacts with water forming sodium hydroxide and urea. However, this can be easily formed in liquid ammonia by reaction of urea with sodamide. When urea NH2CO NH2 reacts with sodamide NaNH2, giving rise to sodium uride and ammonia. Acid-base reactions. Acid-base reaction can be explained on the basis of solvent system concept. Generally, when acid reacts with a base to form salt in water is called neutralization reaction. So, these acid-base reactions can be explained on the basis of solvent system concept. An acid is a substance that by direct dissociation or reaction with a solvent gives the cation, characteristic of the solvent. Similarly, a base is a substance that gives the anion, characteristic of the solvent. For example, in liquid ammonia solvent, NH4 plus ion acts as acid and NH2 minus ions act as base. The neutralization reaction is NH4Cl plus NaNH2 gives rise to NaCl plus 2NH3. In this reaction, NH4Cl is called acid. Why? Because according to solvent system concept, any substance which produces NH4 plus ion in liquid ammonia is called acid. Similarly, any substance which produces NH2 minus ions in liquid ammonia is called a base. Therefore, NH4Cl ammonium chloride is called an acid. Sodamide NaNH2 is called a base. Solvolating reactions or solvolysis. Solvolating reactions or solvolysis. The reactions in which the solvent molecules react with the solute in such a way that the solvent molecules split up into two parts, one or both of which get attached to the solute molecule or ion are called solvolytic reactions. Now, water as solvent. When water undergoes autoionization, it produces H3O plus and OH minus ions, hydronium ion and hydroxide ion. Similarly, sulfuryl chloride SOCl2 reacts with water producing hydronium ion and chloride ion. Fluoride ion reacting with water producing hydrogen fluoride and OH minus. Ammonia as solvent. Ammonia undergoes R2 ionization producing ammonium ion and amide ion. Sulfuryl chloride reacts with 4 ammonia molecules producing ammonium ion and chloride ion. Hydride ion combines with ammonia forming amide ion releasing hydrogen. Solvation reaction. Solvent get attached to a solute species, cation, anion or molecule are called solvation reactions. The species formed is called solvate. Example, CuSO4 plus 4NH3 gives rise to CuSO4 4NH3 ammoniate. CuCl2 plus 4H2O gives rise to CuH2O taken 4 times 2 plus 2 Cl minus hydrate. BaSO4 plus 3H2SO4 gives rise to BaSO4 3H2SO4 solvate of sulfuric acid. Reactions in liquid ammonia. Reactions in liquid ammonia. Acid-base reactions. Acid-base reactions. Now, liquid-base, acid-base reactions. Liquid ammonia ionizes as 2NH3 gives rise to NH4 plus NH2 minus. For example, potash amide gives rise to potassium ion and amide ion. Protolysis reaction. Certain compounds like urea, which are incapable of donating protons to water, can readily donate protons to ammonia in liquid ammonia. NH2 bond CO bond NH2, that is urea. When urea combines with ammonia, produces ammonium ion. This ammonium ion can lose a proton. So certain compounds like urea, which are incapable of donating protons to water, can readily donate proton to ammonia. Can readily donate proton to ammonia in liquid ammonia. Acid-base neutralization reaction. Neutralization of an acid and base in liquid ammonia involves combination of NH4 plus ion from acid and NH2 minus ion from base. NH4Cl plus KNH2 gives rise to KCl plus NH2NH3. Means in this reaction, when ammonium chloride combines with potash amide, produces potassium chloride. In this reaction, salt is formed. Therefore, we call it as a neutralization reaction. Ammonium chloride is called acid because it can produce NH4 plus ion in liquid ammonia. Potash amide is called a base because it produces amide ion in liquid ammonia. So NH4 plus comes from NH4Cl, NH2 minus comes from KNH2 combined to produce 2NH3. As an acid, zinc hydroxide reacts with potassium hydroxide forming a salt. As a base, zinc amide reacts with ammonium chloride producing zinc chloride and ammonia. Precipitation reactions. Precipitation reactions involve double decomposition because of the differences in solubilities. KCl plus AgNO3 gives rise to AgCl plus KNO3. Already I told you, in precipitation reaction, double decomposition reaction takes place. White PPT of PaCl2 is produced when silver chloride and liquid ammonia brought together When silver chloride and barium nitrate are brought together in liquid ammonia produces barium chloride as white precipitate. Ammonolysis reaction. The solvolysis reactions in liquid ammonia are called ammonolysis or ammonolytic reactions. For example, hydrolysis of silicon tetrachloride occurs as silicon tetrachloride undergoes hydrolysis producing silicic acid. Organic halides undergo slow ammonolysis reaction to form amines. RX is alkyl halide when alkyl halide reacts with ammonia producing primary amines. Solutions in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metals. It means alkali metals are readily soluble in liquid ammonia. When alkali metals dissolve in liquid ammonia form blue colored solution. The resulting solutions are blue in color and the blue colored solutions are good electrical conductors. When alkali metals are dissolved in liquid ammonia, they ionize to give metal ions and valence electrons, as Na gives rise to Na plus E minus. Both alkali metal and become solvated by ammonia molecules. Na plus combines with X number of ammonia molecules forming ammoniated cation. Electron which is released from Na atom combines with Y number of ammonia molecules forming ammoniated electron. The complete reaction may be written as Na gives rise to Na plus NH3 taken X times plus, that is ammoniated cation and ammoniated electron. The ammoniated electrons are responsible for blue color of solution. The ammoniated electrons are responsible for blue color of solution and the ammoniated electrons are also responsible for the electrical conductivity of blue solution. Thank you.